Welcome to Biogas Basics. My name is Jürgen Kube, and today's presentation is about the stoichiometry of the AD process. From the simple beginnings of Buswell and Boyle to the impact of biomass buildup on the biogas yield and composition and the calculation of the heat of reaction. Most people working in the biogas industry have heard of the Buswell formula. The Buswell formula describes the stoichiometry of the biogas process. Substrate and water react to methane and carbon dioxide. The formula has three output variables: the amount of water required x1, the amount of methane x2, and carbon dioxide x3 produced. To solve it, three input variables are required: the amount of carbon C, hydrogen H, and oxygen O in the substrate. For clarification, we define substrate as the part of the feedstock that can be fully converted into biogas. Not all of the feedstock is substrate. In the following example, we are going to use vector and matrix notation. We're looking for the unknown output variables: x1, the amount of water required, x2, the amount of methane produced, and x3, the amount of carbon dioxide produced. Before we start the calculation, we subtract the substrate, the methane, and the carbon dioxide from both sides of the equation, and then multiply everything with -1. Now the substrate is on the right-hand side, whereas water, methane, and CO2 are on the left-hand side of the equation. We start with the carbon balance. Water, which is x1, doesn't contain any carbon. Methane and carbon dioxide have both one carbon each, so the first row is 0, 1, 1. On the right-hand side of the equation is the carbon content of the substrate C. Next row is the hydrogen balance. Water contains 2 hydrogen, but it is an educt, hence it gets a negative sign. Methane in column x2 has 4, and carbon dioxide 0 hydrogen, so the second row is -2, 4, 0. On the right-hand side of the equation system is the hydrogen content of the substrate H. The last row is the oxygen balance. Water has 1 oxygen. Because it is an educt, its stoichiometric coefficient is -1. Methane has no oxygen, hence the second column entry is 0. CO2 has 2 oxygen, so the last row is -1, 0, 2, and on the right-hand side of the equation system is the oxygen content of the substrate O. Now to get to the unknown vector x, we must multiply the inverse of the matrix to the inhomogeneity or right-hand side. The solution is shown here. We can now calculate x1, x2, and x3 as a function of C, H, and O, the composition of the substrate. And then we can insert the factors into the equation above, and what we get is the Buswell formula. Let's see which information we can derive from the Buswell formula. Let's start with a simple example: starch or cellulose. Starch and cellulose are biopolymers. Each subunit has the formula C, 6H10O5. It reacts with 1 molecule of water to 3 molecules of methane and 3 molecules of carbon dioxide. So right from the start, we can see that biogas from starch or cellulose contains 50% methane and 50% CO2. Now let's look at the mass of each reactant. 1 unit of starch weighs 162 grams, plus 1 molecule of water, which is 18 grams, reacts to 3 molecules of methane, which is 3 times 16 gram or 48 gram, and 3 molecules of CO2, which are 3 times 44 gram or 132 gram. The mass on both sides of the equation adds up to 180 grams. It takes 18 grams of water to create 180 grams of biogas. So 10% of the biogas mass comes from water and 90% comes from substrate. When we talk about gas, it makes sense to use volume units. In total, 6 molecules of gas are produced. 1 mole of gas has a volume of 22.414 liters at reference conditions. We use 0 degrees Celsius and 1 atmosphere here. In total, 134.5 liters of gas are produced. We can now calculate the biogas yield: 134.5 liters divided by 162 grams, which is the mass of the original substrate. This gives the biogas yield of 830 cubic meters per ton. At this point, I would like to point out that when working in the biogas industry, every volume statement should always refer to a reference state, pressure and temperature. Without the reference state, the information regarding volume is more or less useless, because we could easily have a ±10% error just by referring to the wrong reference conditions. So always state your reference conditions when you give any volume information. The reference condition I've used here are called norm cubic meters, and these are widely used in Western Europe except for UK. Back to the starch example. We can now calculate the density of the biogas. We know the composition of the gas, and the density of an ideal gas is the reference pressure times the average molar weight of the biogas divided by the gas constant in the reference temperature. In this case, the density is 1.34 kilograms per cubic meter at norm conditions. Let's recap what we've learned so far. With the Buswell formula, we can calculate the yield, composition, and the density of the created biogas. Further, we can see that the Buswell formula is unambiguous. There is a unique result for yield, composition, and density for a given substrate composition. No process modification, magic powder, or snake oil can change that. So if someone promises yields above the stoichiometric limit, or a certain supplement that increases the methane content of the produced biogas, red flags should be raised. The Buswell formula can be expanded by nitrogen and sulfur. This is known as the Buswell and Boyle-formula. Now, we have two additional input variables, the nitrogen and sulfur content of the substrate, and must create two more output variables. Nitrogen is reduced to ammonia, and sulfur is reduced to H2S. Again, we balance each species and then invert the matrix to calculate the factors in the Buswell and Boyle formula. We can see that the presence of nitrogen and sulfur in the substrate increases the water demand used in the hydrolysis of the substrate and the CO2 content of the produced biogas. It decreases the methane content of the biogas. Personally, I'm not a big fan of the Buswell and Boyle formula. I think it has mostly academic uses. The conversion rate of nitrogen and sulfur is unknown, and some of the sulfur will precipitate as ferrous sulfide. But most importantly, the incorporation of carbon, hydrogen, oxygen, nitrogen, and sulfur in microbial biomass is not considered in the Buswell and Boyle formula. For this, we need to go back to the basic reaction of the biogas process. Substrate and water reacts to biogas, microbial biomass, ammonia, and H2S. The exact composition of microbial biomass varies from strain to strain, but on average, it consists of 54% carbon, 25% oxygen, 10% hydrogen, and 10% nitrogen, and 1% sulfur by mass. We can calculate its molar composition by setting carbon to 1. The rest is H, 2.22, O 0.347, N 0.159, and S 0.007. Now we can write substrate plus X1 water reacts to X2 methane plus X3 carbon dioxide plus X4 ammonia plus X5 5H2S plus Y biomass. We can calculate Y with the yield coefficient YXS. It is defined as the mass of biomass produced divided by the mass of substrate consumed. The yield coefficient is around 8% in the AD process. Why 8%? The substrate will have to pass at least through the acidogenic step and the methanogenic step. The acidogenic bacteria usually have a yield coefficient of around 5%. They generate more energy per consumed carbon and can create more biomass. The methanogens have a lower yield coefficient of around 3%. Together, the AD process will have around 8% as a yield coefficient. We can directly calculate the parameter Y, which is a constant. It depends only on the yield coefficient and the molar mass of the substrate and the microbial biomass. The amount of carbon, hydrogen, oxygen, nitrogen, and sulfur incorporated in the microbial biomass is constant and can therefore be moved onto the right-hand side of the equation, so it appears in the inhomogeneity. In the next step, we balance every species and invert the matrix. The result is shown here. Again, we can now calculate the biogas yield and the biogas composition and density. We will look at some examples in a minute, but before we do that, we can use this formula to calculate the heat of reaction of the biogas process. For this, we will use Hess's law. We will need the upper calorific value, or CV, of all reaction species, and we must ensure that they are in the right phase. The reaction is substrate plus water reacts to methane, carbon dioxide, ammonia, H2S, and biomass. Water and CO2 have a CV of 0. We can use literature correlations, for example Boy, as shown on the screen, to calculate the CV of substrate and biomass based on its stoichiometric composition. The upper CV of methane gas is known, negative 891 kJ per mole. We also know the upper CV of ammonia, negative 383 kJ per mole in the gas phase. The biogas reaction takes place in the liquid phase, so the gaseous ammonia will have to dissolve in the aqueous phase, where it will mostly dissociate to ammonium. The heat of solution and dissociation are given on the screen. The physical properties used here are for reference conditions of 1 bar and 25 degrees Celsius. Now that we have all the formulae, let's calculate the biogas properties of some commonly used feedstocks. The following table shows the carbon, hydrogen, oxygen, nitrogen, and sulfur content of the substrate. the molar mass of the substrate in gram per mole, the amount of water required for the hydrolysis of the substrate in mole, and then the reaction products: methane, carbon dioxide, ammonia, H2S, and biomass in mole. The next column shows the water demand of the hydrolysis as a mass fraction. That is the mass of water required per mass of biogas produced. Then comes the biogas yield in cubic meters per ton at the reference conditions of 1 atmosphere and 0 degrees Celsius. The next columns show methane content and the density of the biogas, followed by the calorific value of the substrate and the heat of reaction of the biogas reaction. The last column shows the ratio of the heat of reaction to the calorific value of the produced methane. Let's start with some carbohydrates. I've given the composition of glucose, starch, or cellulose, sucrose or lactose, pectin, and arabinose here as an example. We used starch and cellulose as an example to explain the Buswell formula. The water demand of the hydrolysis was 10%, the biogas yield was 830 cubic meters per ton, and the produced biogas consisted of 50% methane. Let's see what happens if we consider the biomass buildup. The water demand of the hydrolysis drops from 10% to 8.4%. The biogas yield drops from 830 to 749 cubic meters per ton, and the methane content of the biogas drops slightly from 50% to 48.6%. The heat of reaction of the digestion of starch on cellulose is roughly 5.5% of the upper CV of the generated methane. The next group are small molecules: ethanol, acetic acid, propionic acid, and butyric acid. They show good gas yields and high methane content, especially for longer chain volatile fatty acids in ethanol. Stearic acid and glycerol are both components of fat, which is also shown here in the form of tristearin. Stearic acids and fat are characterized by very high gas yields and high methane contents. They also require a lot of water in the hydrolysis step. Roughly a third of the biogas mass originates from water. Glycerol is a readily available feedstock which is a byproduct of the biodiesel production. It is one of the few substrates that produces water during the biogas process, whereas most substrates require water for the hydrolysis of the substrate. Its biogas yield and methane content are only moderate. It is often overestimated because glycerol reacts very quickly and violently to biogas if added into a digester, and is generally considered a very good substrate, albeit it can be contaminated with sulfuric acid and create H2S in the process. The molecules we have discussed up till now do not contain any nitrogen. However, as these substrates are consumed, microbial biomass is created, which consists of 10 mass% nitrogen. As a result, the formula gives small negative numbers of produced ammonia. Ammonia is consumed during the fermentation of nitrogen-free substrates like carbohydrates. The next group of substrates does contain nitrogen. Alanine is one of 20 amino acids shown here as an example. Bovine serum albumin is a protein which can be separated from the blood serum of cattle. It is widely available and is used as an exemplary protein here. The next row shows the composition of the microbial biomass, which I use in the stoichiometry of the biogas process to describe the biomass buildup. I've normalized the formula so that I set sulfur to 1 and then all other species can be shown as integers. The degradation of protein is usually characterized by a very high water demand of the hydrolysis. Protein consists of amino acids which are connected via peptidic bonds. Splitting this bond requires water. Amino acids are usually small molecules. The average molar weight of all 20 natural amino acids is only 119 grams per mole, and that is after the peptidic bond has been cut. A large amount of water is required to hydrolyze the protein and generate biogas. In this example, more than half of the biogas mass comes from water, and the biogas yield is also quite high. For the next group of substrates, I looked up the elemental composition of maize, lignin, and chicken muck and computed the substrate properties purely based on the stoichiometry. Maize contains 3% lignin in the dry matter. Lignin cannot be converted into biogas. We have to subtract the lignin content from the maize to compute the biogas properties of the digestible part of the maize. The computed values match literature values quite well. The computed biogas yield for maize is 757 cubic meters per ton, whereas the literature value is roughly 750 cubic meters per ton. The computed methane content is 51.1%. In reality, we measure around 52%. The computed water demand for the hydrolysis is 13%. In reality, we measure slightly lower values of around 5%, and the heat of reaction is roughly 4.4% of the calorific value of the produced methane, which is close to experience values. The computed values for chicken muck are considerably higher than literature values. The literature value for the biogas yield is around 500 to 550 cubic meters per ton. The computed biogas yield of chicken muck is 795 cubic meters per ton. Unlike maize silage, chicken muck contains a large percentage of inert organic dry matter, around 30 to 36% based on the comparison of the literature and computed biogas yields. The elemental composition alone will not give any information about the content of inert organic dry matter. The last substrate I'm using here is urea. I use this as an example for exotic feedstocks, which properties can also be computed with the expanded Buswell-formula. Urea has a low gas yield of around 293 cubic meters of biogas per ton, but the methane content is minus 17.3%. That means that while urea produces biogas, it produces only CO2, and it will further reduce the methane production from other substrates in the reactor. Lastly, I want to talk about the chemical oxygen demand, or COD. The chemical oxygen demand is the amount of oxygen that is required to completely oxidize a substrate. It is given in gram oxygen per volume of sample, for example milligrams per liter. The formula of the oxidation process is shown here. Substrate and oxygen react to CO2 and water. It can be compared with the Buswell-formula. Substrate and water reacts to methane and CO2. Both formulae show a similar term for oxygen demand and methane production. The amount of oxygen required to oxidize the sample, the chemical oxygen demand, is linked to the amount of methane that can be produced from the substrate. We can see that if we visualize the reactions. Substrate can either be oxidized directly to CO2, or it can be fermented to methane and CO2 first, and in a second step the methane can be oxidized to CO2. Both pathways lead to the same outcome, CO2, and require the same amount of oxygen. We can write the oxidation of methane. In total, 2 molecules of O2 are required to oxidize 1 molecule of methane. 1 molecule of methane at the reference conditions of 1 atmosphere and 0 degrees Celsius are 22.414 liters. 2 molecules of O2 weigh 64 grams. We can calculate the ratio of the two values, which is 350 cubic meters of methane per ton of oxygen demand or of ton of COD. We do not get any information about the amount of carbon dioxide that is produced in the process, or the water demand of the hydrolysis reaction. The value of 350 cubic meters of methane per ton of COD is an upper limit. It does not consider biomass buildup, maintenance metabolism, transport energy, or inert or recalcitrant parts of the substrate. The COD gives the best case methane potential. In reality, the methane yield will be lower because some of the energy is used to build up and maintain the biomass, or to transport substrate molecules into the microorganisms. We can compute a COD organic dry matter ratio, which will give us information about the feedstock composition, namely the average degree of oxidation of the feedstock. Fats, for example, have a ratio of about 4 grams of COD per gram of organic dry matter, whereas sugars have a ratio of around 1.1. COD is mostly used in wastewater plants. Sometimes it is also used in food waste AD plants as an easily measurable indicator for the methane potential of the food soup or waste suspension. In this case, remember, it is an upper limit and not the real methane yield. Biogas yield, biogas composition, the hydrolysis water demand, and the biogas density are a function of the stoichiometry of the degradable part of the substrate, and can be calculated with the Buswell-formula. The Buswell-formula can be expanded by nitrogen and sulfur. The so-called Buswell and Boyle-formula is mostly of academic use as it does convert all nitrogen to ammonia and doesn't consider nitrogen incorporation during biomass buildup. The Buswell and Boyle-formula can be extended by biomass buildup. The composition of the biomass and the yield coefficient in gram biomass produced per gram substrate converted must be known or estimated. The extended formula leads to reduced biogas yields and water incorporation. The extended formula can also be used to estimate the heat of reaction. For carbohydrates, the heat of reaction of the biogas process is around 5% of the upper calorific value of the produced methane. The stoichiometry is a good start to estimate substrate properties if no gas yields are known. But the percentage of inert organic dry matter in the feedstock is important to estimate the gas yields correctly. COD can be used to quickly estimate the methane yield of a liquid substrate, but it overestimates the yield and gives no information about the biogas composition or the hydrolysis water demand. This concludes my presentation about the stoichiometry of the biogas process and all the information that can be derived from it. I hope you learned something new, and I see you in the next episode of Biogas Basics.